The barber shaves all those and only those who cannot shave themselves. So my question is, who shaves the barber? Okay, I give you guys 2 minutes to think about this. So I repeat the question once. In a town, there is only one barber. The barber shaves all those. Okay, I'll just capitalize this. Shaves all those and only those who cannot shave themselves. So who shaves the barber?
Dada, isn't the statement a bit something false?
Yes, the statement is what?
1 minute.
Okay.
Does the statement contradict itself?
Yeah, it's
How so?
contradicting each other. The barber can't shave himself.
Okay, the barber can't shave himself, so can someone else shave the barber?
No, because only there's only one barber.
Okay, let's no. Suppose everybody can shave. I mean, not everybody can shave, but I mean, shaving is not very complex. You don't need to be a barber to shave someone. I mean, you can suppose that there are some people who can shave themselves.
Can I say something?
Okay, yeah,
Uh, the if the barber, suppose the barber does not shave himself, so
yes,
he is among those who cannot shave themselves. So he can
yes.
shave himself, but if he does, then he becomes one of those who can shave themselves. But then if he doesn't, he is again someone who does not shave themselves, and so it is a paradoxical situation.
Yes, exactly. It's a paradox. And I tell you why we've come to this question now, later on. So the solution goes like this.
I didn't know the solution, but I knew the question. It is the barber's paradox by
Yes, yes,
Bertrand
Yes,
it's
Russell.
a
yes,
pretty
Barber's
famous.
paradox.
By Bertrand Russell.
Yes, it's a pretty famous paradox. We'll come to this later on. So the solution is, suppose the barber doesn't shave himself. So we have only two options, right? This is one option, doesn't shave himself and shaves himself. So suppose the barber doesn't shave himself. So the barber shaves those and only those who cannot shave themselves.
So means
Right.
Biden knows how to shave.
Yes, exactly. So that's a contradiction. And if the barber does shave himself, what happens?
Then he's one of those who cannot shave, but he at the same time he's shaving also. So again a
Yes,
contradiction.
exactly. So we have a contradiction here, and this is known as Russell's paradox. Russell's paradox, named after Bertrand Russell.
Can you again explain the contradiction?
Yeah. So suppose the barber doesn't shave himself. Right.
Okay.
এই শোনা যাচ্ছে তো?
The video went off.
Yes, Dada.
আচ্ছা।
Now we can see your thumb.
Okay, can you see the full board again?
Yes, yes.
Okay, so suppose the barber doesn't shave himself. Now, what is the role of the barber? The barber shaves those and only those who cannot shave themselves. So the barber is compelled to shave himself. So here we have a contradiction. And now the second case is the barber does shave himself, but the barber shaves those and only those who cannot shave themselves. So if the barber does shave himself, that's a contradiction again because he can shave himself.
In both the case, there are the superposition of two events. Means he can shave and he cannot shave.
Yes, exactly. So
Why?
it's both true and false.
How are you contradicting that he doesn't shave himself? That contradiction. First one.
Okay, so suppose the barber doesn't shave himself.
Yes.
Now the barber shaves all those. Now we are focusing on the word all. The barber shaves all those who cannot shave themselves. So if the barber doesn't shave himself, the barber is compelled to shave himself.
Okay, okay, I understood.
Right. That's why I was stressing on the two words, all and only. So all those and only those who cannot shave themselves.
Okay, okay, I understood.
There's a reason I started with this. This has some sort of a significance in set theory, and we'll move on to that later. Okay, so today we are not going to talk about any Olympiad type
Dada,
topic. Yes.
acha, to the for, this question, Barber one, one case could be that there are people who cannot shave themselves but can shave others.
No,
You
the
can
two
ask.
cases are the barber shaves himself or the barber doesn't shave himself.
But in this question, it's written he shaves all those.
Yes. This question is basically who shaves the barber. So there can be either of two cases, right? Either the barber shaves himself or someone else shaves him. In which case the barber doesn't shave himself. So in either of in both the two cases, you will get a contradiction, which is why it's a paradox.
Okay.
Yeah, you can read up more about Russell's paradox. I'll give you a formal definition with sets later on. So today's topic was language of mathematics. I don't know if it's entirely accurate, but okay. So in English we have letters, right? We have A, B, C, D, E, F, G up to Z, and we take sets of these letters. So we have these letters. Now we take sets of these letters to form words, right? So we take CAT, we have cat, we have math, and we have words like that. Now this forms your vocabulary, right? So you take many words, the words you know that constitutes your vocabulary. Now if you string together these words, the cat is on a roof. So here you're taking words and you're stringing them together logically. So that's your grammar. So instead of on, you can't just write cat is in a roof. That would be wrong grammar. So basically English is a structure. It's a structured language. So suppose if I call you an idiot, you get offended, right? Because you map idiot to some certain negative quality. So suppose you take idiot. You map idiot to say dumb, low intellect, stuff like that. But if I call you, suppose, a genius, that makes you happy because it maps to certain positive quality. If I say genius, it maps to say smart, high IQ, etc. Now these are just definitions. So tomorrow, idiot could mean smart and high IQ, and genius could mean dumb and low intellect. So by that logic, I have become a genius. So basically, these are just definitions. And in math also, we have definitions, we have vocabulary, we have grammar, which makes certain things impossible. Like 1 plus 1 equals 3. This statement is impossible. And why it is impossible? It's because the entire system of numbers is based on certain axioms, which prevents this from happening. Now I will discuss these axioms known as piano axioms later on. Now we'll move on to perhaps the most fundamental part of math, something which we frequently ignore in school. For some reason, schools don't teach set theory in depth a lot. But set theory forms everything. Set theory is the foundation of everything, most things in math. A combinatoric. What is a permutation? A permutation is a set of some elements. It's a rearrangement of a set. Take geometry. What is a line segment? A line segment is a set of points. Right? And so on and so forth. Group theory, say groups, rings, fields, everything is based on set. So, what is a set? A set is a collection of objects, right? Now, somewhere around 1870, George Cantor and Richard Dedekind so these two guys came up with the first form of set theory that we come to know of, and that is naive set theory. So they came up with this set theory, which is naive set theory.
Your video is blurry.
Larry. Is it better now?
No, the writings are not readable.
It's not clear.
Can't
Na?
read what you have written.
Okay, give me a sec.
We can't hear you.
Okay, can you see the board now? More clearly.
No, Dada.
এখনো can you see from here? It's not clear. The writing.
The board is not coming.
Your video is off.
Yes, Dada, your video is off.
এখানে দেখাচ্ছে on. What about now?
You can see it.
Now it's visible. Now it's visible completely.
Okay, great. So around 1870, George Cantor and Richard Dedekind came up with naive set theory. So naive set theory was set theory in its most primitive form. So why don't we study naive set theory? It's because it has some loopholes. And we discussed one such loophole like 10-15 minutes back. And that is Russell's paradox. Now, how exactly does that work? So they said that a set is any definable collection of objects. So they said that a set is a definable collection of objects. Now Bertrand Russell came up with this. Suppose you have a set R X such that X doesn't belong to X. So what does this mean? This means that suppose you have a set R and R is a set of all sets which are not members of itself. That definition is a bit confusing, I know. So I repeat it. R is the set of all sets which are not members of themselves. Now look at R.
Themselves means the elements, or that themselves mean the not elements of the R.
The set itself.
Oh, means suppose X is a set, X does not contain the element X.
Yes. So now take the set R. Now R is the set of all sets which are not members of itself. So if R is in R, then that's a contradiction, right? By the definition of R. Because R can't be a member of itself by definition. Now suppose R is not a part of the set, but by definition R is the set of all sets which are not members of itself. So R must be in the set.
Is that a belong to sign with a cross?
Belong to sign with a cross. Yes.
I didn't understand the thing.
Okay, so did you understand the Barber paradox?
No, not quite really.
Okay, you should definitely check out the Barber paradox. So I'll explain this once again. Suppose R is the set of all sets which are not members of itself. Now we take R. Suppose R is a member of R, but by definition R is not a member of itself. So R can't be in R and R can be in R and R can not be in R simultaneously. So we have these two things happening simultaneously. We have R belongs to R and R doesn't belong to R. Both of these can't happen together, right? A statement cannot be true and false. It can be true or false. So Russell's paradox was the first, not the first, but one contradiction in naive set theory, which is why the set theory that we now know of and usually follow
Can you just explain how this loophole is related to the Barber's paradox once?
Okay, so basically the Barber paradox is an analogy of this. So here instead of the Barber, we are taking this set R. Now these two statements are both true and false. The Barber, suppose the Barber shaves himself. So then we get the contradiction that the Barber has to shave himself and the Barber can't shave himself. So we have a true and false statement. Here as well, R has to be in R and R can be in R. These two are happening simultaneously. So it's basically a true and false condition. Okay, so coming back to this, the set theory that we now know of and use mostly, that is known as the Zermelo-Fraenkel set theory plus the axiom of choice. So the axiom of choice is another pretty interesting thing, and I won't touch upon this a lot, but you can read up on this. The axiom of choice in simple terms says that suppose you have several sets. The axiom of choice says that you can create another set constituting each one element from every such set. So suppose you have a collection of sets
From the each one element from the
from all the sets. So suppose you have a collection of sets. So the axiom of choice says that you can create a set. So suppose we set S, you can create a set S by taking one element from each of these sets. So this is a very watered down definition of what the axiom of choice is, and we denote it by C. We denote axiom of choice with C, and we call this ZFC.
ZFC.
Yes. We also have Zermelo-Fraenkel set theory without the axiom of choice, which we call ZF minus C. The axiom of choice is a pretty controversial topic. So,
ZF minus
ZF minus C means without the axiom of choice. Usually we consider the axiom of choice when we are doing math.
Dada, now your video is becoming hazy.
but it's fine.
You can read it.
Yeah, set theory.
Okay, yes, then it's fine. So, basic operations of set. Most of you know this, but we'll just do a quick recap of this. So, how is an element related to a set? So, suppose you have an element E. You have an element E, and you have a set S. So, there's a binary operation between this element E and this set S. That is, E belongs to S or E doesn't belong to S. So either an element is a member of the set or it's not a member of the set. There's also a pretty interesting variation of another branch of set theory known as the fuzzy set theory. You can read up about this if you want. It's called fuzzy set theory.
Spelling?
FUZZY. So this basically says that usually what happens is an element is either in a set which we denote by 1 or the element is not in the set which we denote by 0. But here you have, it can be any real number between 0 to 1 both inclusive. So suppose you have a set of tall boys. So it's not like you're 0 or 1. It can be something like
Are you
0
talking about the principle of superposition? Superposition.
not exactly.
That quantum one Schrodinger's cat experiment.
Now what on, but you can read up about this if you want. If you can't. Okay, so most of you know set operation. So suppose you have a set A and suppose you have a set B. You guys know that A union B is the set of all elements in A or B. You know that A intersection B is the set of all elements in A and B. So this is A or B. This is A and B. You have A, B. This means elements in A, not in B. And you have the symmetric form. So A, this denotes elements in only one of A and B.
But yeah, till A union B and A intersection B, it's visible. Oh, now it's visible. Shadows come.
Okay. So you have A minus B actually. So elements in A, not in B, and then you have the symmetric.
But yeah, in the third operation, what's the symbol is not visible?
It's a slash.
And in the fourth one?
The fourth one, it's a triangle. It's a symmetric difference. ए बाबा की स्लैश दिला बेटा sorry ए बाबा okay now it's correct elements in A not in B and the next one is the symmetric difference which means symmetric difference is basically so symmetric difference is which is denoted by a delta. This basically means A minus B union B minus A.
That means intersection B.
You're breaking up a bit. Could you repeat again?
Does it mean that A union B minus A intersection B?
Exactly, yes. Another form in which you could write this is A union B minus A intersection B.
What is the sign of the third one? That elements you
Third
are
one is
talking
a slash,
Okay.
a forward slash.
Isn't it written minus? Because in some books they have written they write minus.
Yeah, some books write minus, but this is the proper notation.
/1.
Slash, forward slash. So apart from this, we also have the Cartesian product. So what's the Cartesian product? So suppose you have two sets. Set A is say A1, A2 up to AN, and set B is B1, B2 up to say Bn. Now the Cartesian product of A and B is
Still
denoted
with
by A.
and one.
Yes, it means all possible ordered pairs of the form AI BJ. So you have A1, comma B2, B1, A1, comma B2 up to A1, comma Bm. Then you have A2, comma B1, A2, comma B2 up to, and so on and so forth up to An, comma Bn. So this is your Cartesian product of A and B. So all possible ordered pairs where the first element is from A and the second element is from B. And you also have the power set. Most of you know what the power set is. Power set is set of all subsets of suppose S, and this includes the empty null set and S. These are inclusive. So suppose there are n elements in S. Can you say how many elements there will be in the power set?
2 to the power n.
Yes.
We did it in combinatorics.
Yes, we did it.
Okay, great. So I don't need to repeat that. And you also know what a subset is.
Yeah, suppose A is a set A1, A2 till AN, then A1 can be there, A1, A2, then A1, A2, A3.
Yes, these are subsets. So
Or, or simply
if we have,
NC0 plus NC1 till NC.
yes, yes. So suppose we have two sets A and B, then we say that A is a subset of B if and only if all elements in A are in B. So this is a proper subset. This is this means that A can be equal to B as well. It's like less than and less than equal to.
Can you, means the A can be equal to also the subset B.
Yes, it's like less than equal to, but instead.
But that will result when A is the subset of B and B is the subset of A.
If A is a subset of B and B is a subset of A, then there can be only one conclusion.
A equal
A
to
is
B.
equal to B. Yes.
Yeah.
So suppose you have A is a subset of B and B is a subset of A. This implies that A is equal to B. I leave this proof to you guys. It's a pretty easy proof.
When will we rejoin?
এটা কি শেষ হয়ে যাচ্ছে নাকি? Is this session ending soon?
Power set. Dada,
Hmm.
can you please explain the power set again?
Okay, power set is basically all the subset of a set. So okay, I'll show this with an example.
Okay.
Suppose
That
X
will
is
2 to the power 10.
one. Yes. Suppose you have the set 1, 2, 3. Then the power set contains null 1, 2, 3
Okay, it contains all the subsets of the set.
subsets, including the set itself. Okay, so I want to write this.
2 to the power 10.
Yes.
Okay.
I think Juanet did this proof with you guys earlier. Okay, so now we'll move on to mapping. So you have two sets, then what? Mapping. Okay, so where did we stop? I didn't start injective mapping yet, I think.
Dada, at the last you just told we are going to start matrix.
Where did I stop? Could you repeat again?
Dada, you just told we are going to start the topic matrix. You didn't start.
Oh, acha. Okay, so we are going to be talking about mapping now.
What?
Mapping. So, what exactly is mapping? I'll tell you. So, suppose you have a set A, and you have some elements in A, and you have a set B. These are some elements as well. Now, you define some sort of a relation from A to B.
Your video is
Suppose
off.
the
Yes, Dada, your video is off.
of okay, what about now?
For a bit it came and then again went off.
Okay, now?
Just now it is okay.
Okay. So, what exactly is a mapping? So, suppose you have the set A and you have some elements in A, and suppose you have the set B and there are some elements in B as well. Now, we define some sort of a relation from A to B.
Are you describing function?
Yes, it's a function. So, suppose you have A1 over here, we perform phi on this, and it maps to say phi of A1. Phi of A1 is in B. So you have A2, A3, A4 like that. A2 maps to something in B, phi of A2. A3 maps to suppose phi of A3, and so on. So I show this with an example that will be more clear to you.
The use of this?
Yeah, I'll come to that. So suppose you have the set S. S is suppose 1, 2, 3, 4. And we define the function as fx equal to x square for all x belonging to S. So here we have
So one
set
four,
S. Yes, you were saying?
so then we will have 1, 4, 9 and 16.
Yes.
So
You have-
suppose that operation is 5, then 1 will be mapped to 1, 2 will be mapped to 4, and 3 to 9, so on.
Exactly, yes.
Can probably map to 16.
So 1 is mapped to 1, 2 is mapped to 4, 3 is mapped to 9, 4 is mapped to 6. And we are performing fx over here. So mapping is basically establishing a relation from one set to another. So we have many types of mapping. Okay, before we start that, I'd like to just state something.
Can you
We had
repeat
1, 2,
the definition of mapping once more?
okay, yes. So we had x 1, 2, 3, 4, and we had fx equal to x square for all x belonging to S, and we had 1 to 1, 2 to 4, 3 to 9, 4 to 16. So now in this case, we have the function fx. Now we say that the domain of the function in this case is all the values that x can take.
That is the set S.
That is the set S. In this case, our domain is the set S. And by range, we mean all the values that fx can take, which in this case is t. So the range is t. So fx is a function which has domain S and range t.
The domain into range.
We can denote it by
Bhaiya, can a single value be mapped to two values?
It can be mapped. If you
When
map
it is
it,
a
it's a kind of
relation.
relation. Exactly. It's not a function. So
Can you
here it can be
example of such?
graph.
Because in a vertical, suppose in the grass we have studied that
Yes,
the
that
if
vertical
that fails the vertical line test,
vertical
then it's
line
not a
test.
function.
Yes.
So here we'll be mostly dealing with functions. So what's an injective map?
Dada, what did you write? Injective?
Injective mapping. So suppose you have a set A and you have the elements A1, A2, A3, AN, and suppose you have the set B. Suppose it is B1, B2, B3 up to BM. So what we mean by injective, okay, before we say that, I'd like to say another definition, which is codomain. So codomain in this case is B. Now there's a subtle difference between codomain and range. So the range is um, all of the time the range is a subset of the codomain, but the reverse is not necessarily true. So basically, what we have is two sets A and B, and now we have a relation from A to B. Now the values that we
Can you
obtain from
again tell what's the difference between codomain and range?
range. So suppose you have the set A and we are applying the function some sort of a relation on A. So the set of all outputs that we get in this case is the range. But B can be more than that. So B is just another set where we are mapping A from where we are mapping A to.
Video went off.
No, Dada.
No, Dada, we can see.
We can see.
We can see. You can continue.
Okay, we'll resume after 2 or 3 minutes. Just give me some. Okay, I'm back. Had some problems with my cat. Okay, so where were we? We were at the difference between range and codomain. So codomain is basically a part of the definition of a function. So if we say that a function is from S to T, then S is our domain and T is our codomain. But T doesn't
Okay,
necessarily
means
have to be the range.
the range depends on the input and the codomain depends whatever that can come.
Yes.
Because if y equal to 2x, then it can the codomain will be 248, and but the range will depend on the input, right?
Uh, so basically, no, the range is just suppose you have the function say fx equal to say suppose you set 2x where x belongs to say 1 to 10. So a range will be 2, 4, 6, 8 up to 20. But the codomain can be anything actually. So the codomain can be all integers from 1 to 50.
So codomain means any integer.
Yes, it can be any
Range
set. But
output.
okay, I'll show this with an example. So suppose you have this function where fx equals 2x and x is in 1 to 5. So in this case, you could take the codomain as set of all natural numbers actually.
Your video
If you
went
went
off.
off. Okay.
Oh, this time I thought it's only for me like the previous.
Okay, so suppose your codomain can be anything actually. So suppose your codomain is set of natural numbers n.
So do
In that
we
case,
define the codomain?
yes,
Because otherwise it would be the universal set.
yeah. So suppose you have your domain over here. So your domain is 1, 2, 3, 4, 5, and your codomain is the set of all natural numbers. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and up to infinite. So you have your codomain over here. Now 1 maps to 2, 2 maps to 4, 3 maps to 6, 4 maps to 8, 5 maps to 10. But there are many other members of this set which are not getting mapped to any element in the domain. So codomain you can actually define as anything, but the range in this case would be 2, 4, 6, 8, 10. This is your range.
Excuse me, Dada, your video is very pixely.
You can't read.
Just see that big set theory, nothing below. Means we
Yes,
can see
but
what very blurry.
it's unclear.
But not
We
much
can
of
just
problem.
see
But
some
as
scribbling there.
even if it's not resolved, even if it's
It
not
shouldn't be
resolving,
much.
it's not much of a issue because you're saying everything, so we can note down.
Okay, so the difference between range and codomain is a bit complicated, but this is the basic gist of it. Codomain you can take to be anything, but range is just the set of values which you get from the
Yeah, we
function.
got it.
Codomain is the universal set.
It's not necessarily the universal set. It can be the universal set.
We can define it as natural numbers also.
You can define the universal set as well. The universal set can be the set of all natural numbers. The universal set can be the set of all real numbers. So, yeah. So, injective mapping. So, suppose you have the codomain. Our codomain is suppose B. Now we have elements from B1, B2 up to Bm. And suppose we have a domain A. This is A1, A2 up to An. Now we say that a function is injective if any element in B maps to only one element in A. So we call an element in B an image. So basically we are doing some sort of a function on A, right? So this function is fx. So what we obtain over here is the image. So suppose f of A1 is equal to B1. So we have a map from A1 to B1. In this case, B1 is our image and A1 we call it the pre-image. So if fx is
Pre-image.
pre-image, yes. So if we have fx equal to y, then y is our image and x is our pre-image. Now coming back to injective, this means that
And where does range
one element an element in the codomain will, an image in the codomain will only have one pre-image. So in formal terms, if x comma y belong to A, then fx equal to fy implies x equal to y.
So Dada, what it is written? If xy belongs to
Which that
A, so if x and y belong to A, then fx equal to fy implies x equal to y. This is your basic statement. Fx equal to fy implies x equal to y, which means that if you have an image in B, then that image has only one pre-image.
mean mapping from one element to a single element, a single element to a single element.
Not exactly. Mapping from, it doesn't mean that A2 has only one map. A2 can have zero maps as well. But if you take an element of an element in the codomain will not have more than one pre-image. So a pre-image can map to one image, or it can map to more images as well. Or if you consider a relation, then it can map to 2 or 3 as well. But here, it can map back to only one. So can you give an example of a function which is not injective? Okay, so a function which is not injective. Suppose,
Can I say
yeah, go ahead.
the sine function, cos function?
Yes, none of these are injective. Why? Suppose sin x over all x. So if you take fx equal to sin x,
Because sine and these functions are cyclic.
yes, x belongs to R. So here you have
So
f of
a single image can have different pre-images.
an image could have different pre-images. Yes. So suppose you have f0 equal to f of 2 pi equal to f of 4 pi equals to 0. So, but this doesn't mean that 0 equals 2 pi equals 4 pi. So, this is not an injective function. Any periodic function can't be injective.
Dada, can you please re-explain why sin x and cos x are
Okay,
not
sin x.
injective?
So, suppose fx equals to sin x. And we'll take this function over all R. So, our domain is R. Now, consider f of x and f of x plus 2 pi. Now, f of x plus 2 pi is equal to sine of x plus 2 pi is equal to sine of x is equal to f of x. So, we have f of x plus 2 pi equal to f of x, but x plus 2 pi is not equal to x. But our definition of an injective function is that if f of x equals to f of y, then x equals to y.
Dada,
That is not the case over here. Yes.
Dada, then will x square minus 3x plus 2 not be an injective function, right? Because it will have x of 1 equal to x of f of 1 equal to f of 2.
Yes, it will not be an injective function. Okay, so now we'll move on to surjective mapping. This is surjective mapping. So we'll consider the same set. So we have A1, A2 up to AN, and we have B, which is B1, B2 up to Bm. Now surjective mapping means, so we have a codomain B, right? So surjective mapping means that every image in a codomain has a pre-image. So surjective mapping means B1 has a pre-image in A, B2 has a pre-image in A, B3 has a pre-image in A, up to Bm has a pre-image in A. So there is not a single image in B which does not have a pre-image in A. So is that clear?
Yes, Dada.
Yes.
Domain has a domain.
Could you repeat, please?
So if we take this codomain as the range, then it will be a subjective. It will be subjective mapping,
It
right?
will be yes. It will be a subjective map. Now an example of this would be, suppose
Fx equal to x and all natural numbers as codomain.
yes, that would be a
If it-
subjective map. So
X,
suppose fx equal to root x belongs to say 1, 4, 9, 16. So you have 1, 4, 9, 16, and here you have 1, 2, 3, 4. So 1 to 1 you have a map, 4 to 2 you have a map, 9 to 3 you have a map, and 16 to 4 you have a map. But this is subjective. But if our codomain was 1, 4, 9, 16, and suppose this is our domain, and suppose our codomain is 1, 2, 3, 4, 5, 6, then 1 has a pre-image in 1, and none of these, 2 has a pre-image in 4, 3 has a pre-image in 9, and 4 has a pre-image in 16, but 5 and 6 don't have pre-images. That means that this function is not surjective, but this function is injective, because these images don't have more than one pre-image. This means that the function is injective but not surjective. And now we'll
But
move
if
on
we
to
take fx equal to root 1 minute.
yes. If we take
Yeah,
fx equal to
if we take fx equal to root x and the codomain as the set of all integers, then it is not an injective function, right? Because 4 can have a pre-image as 2 and minus 2 both. Sorry.
square root will never give a negative value.
Yeah. I just discovered. I was trying to say for y equal to x square. Sorry.
Acha, yeah. Yes, x square if you have
when subjective, every domain value will be there in codomain.
a subjective means that if you have an image, then it will have only one pre-image.
Okay.
An image will not have more than one pre-image. It can be 0 as well, but it won't be more
On
than 1.
be injective.
And now we'll move on to something which we use frequently in combinatorial problems. This is bijective mapping. So bijective mapping is basically injective plus surjective. So what happens if a function is injective as well as surjective? So injective means that each image has not more than one pre-image, and surjective means that every image has a pre-image. So basically you end up with a very nice sort of a relation. So you end up with a very nice relation like this. Sorry, I have an extra over here. So we call this bijective or 1-1 mapping. 1-to-1 mapping. So we call this 1-to-1 mapping. This is injective as well as surjective. So if you take an element over here, it has only one map over here, and vice versa. And all elements have, all pre-images have one image. All images have one pre-image. Basically, you have a nice map. You can use this to solve some pretty interesting questions.
Dada, injective mapping was that if X and Y both belong to A.
If X and Y both belong to the domain, yes.
Okay.
Then Fx equal to Fy implies X equals to Y. Okay, now we'll do a question.
Then how was set B into play over there?
Set B was the codomain.
Oh, acha.
Okay, so we'll solve a question now. So suppose you have n balls. Let Q be the number of ways in which you can put them in K boxes such that each box has greater than equal to one ball. Okay. Now
N identical or N distinct?
Yes, sir, that is
take n identical balls. Okay, I should mention that. Yes. So you have n identical balls. So let Q be the number of ways in which you can put them in K boxes such that each box has greater than equal to one ball. Now let P be the number of ways such that the box with most balls has K balls and all other boxes have greater than equal to one ball. So let Q be the number of ways in which you can put them in K boxes such that each box has more than one ball. Let P be the number of ways such that the box with most number of balls has k balls and all the other boxes have greater than equal to 1 ball. This doesn't mean that there are k number of boxes. There can be any number of boxes. But the box which has most number of balls has k balls. So you need to prove that.
How? But it is but it was in there in the previous statement that there are k number of boxes. Is it not same for the second statement as well?
No, they are two different statements. Let q be the number of ways in which you can put them in k boxes. So you have k boxes, you put n balls in them, such that each box has more than one ball. Now, in the second scenario, the number of boxes is not necessarily k, but the box which has maximum number of balls has k balls. And all other boxes, this doesn't mean that there are total k boxes. There can be k plus 1 or I don't know, k minus 10 boxes as well. And other boxes have more than one ball.
The box which has greater number of balls will have k balls.
The box which has maximum number of balls has k balls. Yes.
Yes. So each box has k balls.
No, the box with maximum number of balls has k balls.
Oh, acha, understood.
So you need to prove that P is equal to Q.
What have you written in the ending part of the second last statement?
Ending part. So let P be the number of ways such that the box with most balls has k balls and all other boxes have more than one ball.
Thank you.
More than equal to one ball.
For the first case, means suppose I'm just confirming. For the P, the number of ways are n minus one, C k minus one.
Yes.
Could you repeat again?
For the
For
first case.
the P, for P, the number of ways is n minus one, C k minus one.
Yes.
N
Not
minus
for P, for
1
Q.
N minus one, C k minus one.
One.
Yeah. It should be n plus 1, k plus 1, I think.
How n plus one?
So
Because there's some k and here the total
okay.
is
It's more than 1. Yes. It's n minus
n
1.
minus one.
All are natural numbers. That's
So now we just need to prove that Q is also this.
Yes, that's one way of solving this.
if the maximum number of balls in one is k, then there can be any boxes in the second case.
Yes, there can be any number of boxes.
Not right.
Okay, so I'll rub this and.
That's one more minute.
Okay. Yes.
Just nearing to the solution.
This is a pretty simple problem, but I want to show you guys a bijective solution. So using bijection, that is.
Can you, I'm using a combinatoric method, but can you tell how to proceed with P? We don't know the number of boxes here.
We don't know the number of boxes in the second part. Yes.
Group n minus k balls into some boxes. So
Yes, we have to. Yeah, we have to allocate n minus k balls. But how?
and the total number of boxes will be k plus.
Less than one less. Hello, Ahirda?
Yes. Yes. Yes.
How to proceed?
Okay. So you're doing via a counting method.
Dada, I
Right?
am doing. Dada, please wait. I am doing.
Okay. Yes. So no, we'll just discuss the counting
Dada,
method.
please wait.
So, yes. Go on, please.
Could you read out the question once? Because it's coming very
Okay.
hazy again.
So suppose you have n identical balls. Let q be the number of ways in which you can put them in k boxes such that each box has at least one ball. Let p be the number of ways such that the box with most balls has k balls and all the other boxes have at least one ball. Prove that p is equal to q.
Dada, then we can get the second one using set theory. That 2 to the power k like that.
Okay. You could proceed like that. Okay, we'll move on to the bijective solution now. So if you have a counting approach, you can send it to me after the session. So the bijective approach is really fun. So we'll write this diagrammatically. So suppose box 1 has A1 number of balls. So we'll write it like this. So some number of balls. So box 1 has A1 number of balls. Box 2 has say A2 number of balls. Box 3 has A3 number of balls. And so on and so forth. Okay, I'll just do another one. Suppose this has 4 balls. So suppose this is your last box. This is the kth box, which has a k number of balls. So if you look at it this way, how many dots do you have? You have k balls. If you
N
look at it
balls,
this way.
total or n balls?
Oh, sorry. Total is n. Yes, total is n number of balls. But how many boxes do we have? We have k boxes, right?
Yeah,
So
k.
if we count this, we get k, right?
Okay.
Yes. And none of these are more than k, right? So if you consider this is k, this is k as well, and none of these can be more than k, right? Because we have only k boxes, so none of these can be more than k. Now, what we are going to do is, so here what is our format? We have boxes, we have the number of balls per boxes arranged in rows. So this is our box 1, this is our box 2, this is box 3, 4, 5 up to box k.
Dada, you are
Now,
doing this for fun, Q or P? Not understand.
I am doing this for the first case, which has q number of loops.
Q, okay.
Okay, so where we have k boxes, A1, A2, A3, none of them are less than 1. So all of them are greater than equal to 1 and we have k boxes. Now, in one step, we'll go from scenario 1 to scenario 2. And that is, okay, can you see the board now?
Yes, Dada.
Okay. So
But
now we
can
should
you
look at
tell
it.
which side to reverse the copy?
Okay, I'm just rotating it, so you don't have to. Okay, so just rotate it like 90 degrees clockwise.
Okay, got it. Yeah, yeah.
Okay, so if you now look at it from here, you have k number of balls. So k, this is k, and
Oh,
no other box has more than k balls.
this translates to the previous question.
Exactly, yes. So this is your bijection in this
And
case.
in this, we are not sure of the number of boxes. In the previous, we are not sure of the
Yes,
number of
exactly.
balls.
But you just have to prove that p is equal to q.
Oh,
You don't even need to find out the number of boxes.
okay.
So
This is
by
very fun, sum.
yes,
Like that,
yes,
we have
I know.
from maximum balls and then
So
It
this
feels like a mystery sum, kind of.
yes. So this is a pretty great example of bijection. We'll do a lot of more combinatorial sums on bijection, but since today it's more on set, we'll refrain from that. Another principle which we often use in mathematical Olympiads is the well ordering principle. So it's the well ordering principle. So the well ordering principle states that you don't need to get bogged down in the terminology. So basically, if you have an ordered set, we call it well ordered.
writing with blue pen.
No, green. So if you have an ordered set, we call it well ordered if there exists a minimum element in that set. So this is the watered down definition that you need to know for now. So this is not a rigorous definition of well ordered principle. So
Can you just
basically,
explain a little bit about this? What does it mean exist a minimum element?
yes. So basically, the well ordering principle says that suppose take the set of positive integers. So we will say that the set of positive integers is well ordered because there is a minimum element in this, right? 1. There is no element in the set of natural numbers less than 1. So
So
we'll say that it is a
suppose
well ordered.
for a ordered set in the natural numbers, each set has to contain one.
The set of natural numbers will contain 1, yes. So it is a well ordered set. But if you take the set of say real numbers, it will not be well ordered because you don't have a minimum element. Suppose
Yes, it will approach
that
minus infinity.
yes. Suppose uh, uh, assume that D is the minimum element of R. Then D minus 1 is even less than D. So contradiction
Then b minus one.
is less than D. So D minus 1 is the minimum element and so on and so forth.
Oh,
So it's a contradiction. Yes,
Madam, should
we'll
we
use this.
rejoin?
Yes, we have a few more topics. One more topic
Someone in the
actually.
chat wrote something about fairy diagrams. Can you explain?
Wait, I'm just checking one. Oh, yes, yes. These are called fair diagrams.
Other
I'll
after you take another 40 minutes.
and not 40 minutes, like 20, 25 minutes. Okay, so
But that
well
solution of this combinatoric problem was really very beautiful.
yes, it's called the Ferrer's diagram. Yes, it's not Ferrari, it's Ferrer. So it's usually it's basically how we represented it, like a collection, a grid kind of thing, where we had like dots like this. This is a Ferrer diagram here. So basically like this. This is a Ferrer diagram. So a pattern with dots like this. Okay, so well ordering principle. So well ordering principle states that if you have a well ordered set, then there is a minimum element in it.
Are you saying something? Cause I can't hear.
No, he's not speaking anything. Dada, are you speaking anything? Dada?
No, he's not
He
speaking.
is, I guess.
I
Yes,
think I think he's thinking he's speaking.
and he couldn't hear.
Oh, Matai.
Yeah. Yes, he's speaking though.
Yes, yes, yes.
Kanida, can you please inform him?
How is he not hearing our voice? That we are telling that we can't hear him.
Aheda, please hear.
He is not connected to the audio. Wait, I'm calling him. I think
Yes.
Khonit bhai is also here. Wait.
Now he will have to explain again.
Your mic is off.
He can't hear.
Actually, he's not connected to the audio only.
Then we can chat him. We can text message him.
Okay, please tell me you can hear me now.
Yes, Dada, but from
Yes,
the
Dada.
beginning of the
Oof.
previous class, we
That's
could
okay.
not
Okay,
hear you. I
I'll
just have
start
to
from the
start
beginning.
again.
Okay, so yeah,
And can you first tell what is the question?
yes. So suppose we have a function such that f of n plus 1 is more than f of n, where n belongs to n. So basically, f is a function from n to n. The domain is n and the range is codomain is n as well. So prove that
N belongs to?
natural numbers n. So prove that f of n equals to f of n is the for all n belonging to n is the only solution. So we have a function from the set of natural numbers mapped to the set of natural numbers such that f of n plus 1 is more than f of n. So proof that f of n is equal to n for all natural numbers is the only solution. A hint is we'll have to use the well ordering principle.
Ahida, are you speaking anything?
No, I'm just waiting for you guys. Okay, so I'll give you guys 1 more minute and then we'll proceed with the solution because we are a bit short on time. Okay, so we'll move on with the solution now. Okay, I'll keep this written. So we have f of n plus 1 more than f of n. So suppose this is our domain and the domain is the set of natural numbers. So we have 1, 2, 3 up to whatever. And suppose this is our range. And suppose our range is a1, a2, a3, dot, 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 dot. And where ai belongs to n. So all of these are natural numbers as well. So obviously, this range is a subset of the set of natural numbers, right? It can be the set of natural numbers as well. So since it is a subset of the set of natural numbers, it is a well-ordered set, and therefore this range has a minimum element. So suppose the minimum element is D.
How
So
is it
minimum
necessary?
element,
Is it necessary it has one?
yes. So
Because
it can't have any elements which are not in N, right?
okay, I
So
got
the
it.
range
It must have
yes,
a minimum element,
yes.
not necessarily one.
Yes. It can be equal to n as well, but it's a subset. We'll just write it for now as like it's a subset. So as it's a subset, it's well ordered and therefore it has a minimum element. So suppose the minimum, yes, what?
Dada, your video went off.
Okay. So suppose the minimum of the range is D. Now D has an image in the domain. Let the image be, sorry, D has a pre-image in the domain. So let the pre-image be M. In that case, f of M equal to D. Now by this relation, we have f of M greater than f of N, M minus 1. So we rewrite this as D. Now here we have a contradiction. We already said that D is the minimum element in the range. So how can this expression be less than D? It cannot be less than D, obviously. So that means
it can
M has to
never
be,
be.
yes, it can't be less than D. So suppose M is more than 1, which means that this function has some value and this will
Yeah,
be something more than D.
Oh yeah, now it came.
Now it's okay, na? Okay, so that means that M cannot be more than 1. Now if M is equal to 1, M cannot be less than 1 as well, because then it's not defined. So if M is equal to 1, then we have F0 over here, which is not defined. And from that we can conclude that M is in fact equal to 1. So M is equal to 1. This means that F1 has the lowest value. So we'll remove D from the range over here. Now take the second lowest element in the range. Let it be D2. Right. So D2 has another pre-image over in the domain. Let it be M2. So if it is M2, then we have f of M2 more than f of M2 minus 1. So we can write this as D2. And so similarly, we'll use the same logic as the previous one, and we can conclude that M2 is equal to 2. So we have f of 2 equal to D2. So M2 cannot be 1, obviously, because this is a function, and M2 cannot be more than 3 or more, because the logic as the previous one follows. So M2 has to be equal to 1. Sorry, yes, M2 has to be equal to 2. So we have F2 equal to D2, and D2 is greater than D1. So this is kind of induction. We are kind of inducting on N
So you
here.
have to M3 equal to 3, M4 equal to 4, then like this.
Yes. So we are getting that F1 is the minimum, then we have F2, then we have F3, then we have F4, and so on. So we have established this via induction. Basically, we are using the well ordering principle repeatedly. Now we'll remove D2 from here and we'll look at D3 and so on. So we have established this. So this means that Fk is greater than equal to K, obviously, because F1, the minimum possible value of F1 is 1. The minimum possible value of F2 is 1 plus F1, which means it has to be greater than equal to 2, and so on. So this means f of k is greater than equal to k. And this also means that, sorry, f of k is, yes, f of k is greater than equal to k. And we also know that f of n plus 1 is greater than equal to f of n. right?
Okay, so here
Brother,
it will be
the
only for
inequality is fixed na? F of n plus 1 greater than f of n hai na?
Miss here f
What?
of n plus 1 greater than equal to f of n, so f of n should be
Oh,
equal
sorry. Yes, yes. We have f of n plus 1 greater than, strictly greater than. I'm sorry. Yes.
strictly greater than fn, so f of n equal to n.
Yes. So can you prove this from here? We have established that f1 is less than f2 is less than f3 and so on. So can you think why f of n is equal to n? Uh,
One में दादा.
okay. Okay, so I'll give you like 1 more minute to try. Okay, since we don't have a lot of time, we'll move on with the solution. So we have established that f of k is greater than equal to k. Now suppose that f of k is greater than equal to k plus 1. So since we have established that f of x greater than f of y implies x greater than y, we have already established that from here. So if f of k is greater than equal to k plus 1, that means that f of k must be greater than equal to f of k plus 1. But that is not true, because our original condition was that f of n plus 1, or replace k n with k. Our original statement was that f of k plus 1 is greater than f of k. So this is a contradiction, right? These two statements are contradictory. And hence, this is false. And hence, f of k is equal to k for all k belonging to n. So we are just using the well ordering principle over here repeatedly along with induction. It's a kind of induction actually.
Was this the last topic today?
We'll move on to something else, and this will be the last topic for today. We won't be able to get into Peano's axiom. So the 1 plus 1 equals to 3 thing will have to wait. Okay, so our last topic is cardinality and accountability.
Other video is switched off.
Dada, your video went off. Hello, is anyone speaking? Hello?
Hello, is anybody there?
Yeah, we are there. Ahirda?